Hello, my name is Jiahe Wang from CS639, and my topic is deep learning microscopy images using deep learning. In the medical field, the clarity of pictures is extremely important for correctly diagnosing diseases such as malaria and cancer. When these images are taken at such a small scale, typically cells and even molecules, mechanical drift occurs and can move the lenses a few micrometers closer or further away from the subject, which makes the picture blurry and can lead to misdiagnosis. It is extremely difficult and expensive to have hardware good enough to counter mechanical drift, so I designed a deep learning neural network in order to accommodate for this. The data I'm using the data I'm using is a dataset of human U2OS cells images, which were taken from the bone tissues of someone with osteosarcoma, a type of cancer. There are 34 types sets containing the same images, with set 0 and 34 being the most blurred and set 17 being the clearest, and used as my ground truth. These were taken at focal length with a 2 micrometer difference between sets. Here you can see what two versions of the same picture at different blur level looks like. So this one is the ground truth, maybe taken from group 17, set 17, and this one might be taken from set 0 or a very small number. The microscopy images I'm using are in TIF format, with only 2 color channels, and they are in 16 bits, so you cannot view them directly on your computers with the default softwares. Each image in the folder represents only 1 color channel, so you have to concatenate the corresponding 2 images together to get a whole cell picture. To make it easier for the computer to process the images, I am separating each picture into 4 pieces, so in each set my model is expected to handle 3072 images. I am using the first 2700 as a training set and the rest as the testing set. And I will start off by introducing the final model. So this is what my model looks like at the end. It is based on UNets. In each UNet, on each convolution layer, I am using the ReLU activation function and then downsampling them until we cannot downsample it anymore. Then I will just upsample it back to the original size, with each layer concatenated with the data kept from the corresponding downsampling layers, as you can see from these arrows connecting each layers. And you may notice that the input I am using for Unit 1 is only 1/4 of resize of the original input, and the input for Unit 2 is only 1/2 of the original input. This is because I designed this model so that the first 2 units are serving the purpose of a pre-train. After running Unit 1, the result would be upsampled twice, so it would come back to the size of 1/2 of the original input picture, and it would be concatenated or added to the 1/2 resize of the original picture, and then used as the input for Unit 2. And for the input of Unit 3, we just repeat this process. And after training from Unit 3, we would yield the eventual result. I also concatenated or add data between the corresponding layers with the same size from different units, because I found out this would produce a better result. So at the beginning of this project, I compared between 3 very popular models used for deep learning, including autoencoder, ResNet, and UNet. Autoencoder had a very bad performance, so I gave up on him. However, UNet performed slightly better than the other 2, so I decided to design an improved model based on UNets. So I did more research and found out an interesting model called teacher-student model, where it has a smaller teacher model serving serving as pre-train, and then the output of the teacher model would be used as the input for the larger student model, which would yield the eventual result. So I built a two-level unit, one smaller serving as the teacher model to pre-train the input, and then the other one which is larger and used as the student model, and it would take the output of the teacher model as its input and then yield the eventual result. And the input for unit 1 was 1/2 resize of the original input, and the input for student model was the concatenate of upsampled output of teacher model and the original out of focus image. However, by comparing the result of that model with the original unit, the improvement was very limited. So I did more research and found out that by adding more connections between different layers and between models, the result is more likely to be better. And thus I added some more interconnections between layers with the same size among the two levels of units. The result had further improvement, which was very exciting. Which was very exciting to me. And then I just thought, what if I build a 3-level of units? And the result was fantastic, and this is why I end up with this model as my final result. To see how well it works, it is a very blurry picture taken from set 0 on this side. It is so blurry that you cannot even tell what it is by just looking at it. However, this is what it looks like after being trained by my model. You can clearly tell that this is a tissue or something taken by a microscope, and I can tell that it is really close to the ground truth. So the way I compare the result between different models is by calculating the PSNR values and the SSIM values, comparing between the output image and the ground truth. So these are the formulas, and this is the algorithm I use to calculate the PSNR and SSIM values. And here's the result comparing between my model with ResNet and some other existing models. This deep deblur is an existing model appearing in someone else's paper that I found out during my research, and this one was the original ResNet. I also tried multi layers of ResNet instead of multi layers of UNet, and however the result was not as good as UNet, as you can see from here, and so eventually my model has the best performance among all the others. So residual means that I'm adding the tensors by the add function, and feature concatenating means that I'm using Keras layers concatenate function. And this is the SSIM value comparison. The difference is more obvious in PSNR comparison, with the same comparing between the same models. And here's a comparison between whether how well it performs if it is interconnected, compared with without interconnections. So you can see the best tools showing in this PSNR diagram are the 3-level interconnected and 3-level interconnected concatenate, these two. Then the 3-level not interconnected version performs slightly better than original ResNet and UNet. For the SSIM, you cannot really see that clearly because the numbers are really close and small, but you can also tell from this blue line that the 3-level interconnected concatenate version is performed the best. And here's the result comparing the output pictures between deep blur and 2 levels of UNet concatenates. So you can see from you can see that at at a more blurry level of the input picture, 3-level of U-Net concatenate would converge faster than the 2-level of U-Net concatenate. And so I'm actually very satisfied with my result, because all the improvements of my models are based on comparisons and observations of the previous result that I get by doing research and testing and calculating. And here's the citation. Thanks for listening.